Hi, welcome to video 7.1b, more on area between two curves. So let's say we have two curves, f of x, which is the blue curve, and g of x, which is the red curve, and they happen to intersect in a few places. Now they're going to ask you for the region bounded by the two curves. The implication here is that this goes up forever, this goes down forever, so this is an open area, not an enclosed region. So they're talking about finding the area of these two green shaded. Now what you'll notice, because we talked about it, we're doing top minus bottom. Here, the function f is on top, g is on the bottom, but on the other side of this point of intersection, g is now on top and f is now on the bottom. So the first thing you're going to need to do is to find those points of intersection. Now, in effect, because we're doing everything in terms of x, you're really only going to need the x coordinates. So, of course, you're going to be given y equals some function f of x and y equals some function g of x. You're going to solve the system of equations. Once you've solved it, you now know they intersect at 1, at 3, and at 7. So, question, of course, is to find the area. As I said, the first thing you're going to do is find the points of intersection. And once you've got the points of intersection, then very simply, it's going to be the integral from 1 to 3, with where f's on top minus g on the bottom, plus the integral from x equals 3 to x equals 7, but this time it's g minus f. The key thing is it has to be top minus bottom. Okay, just a little note for now. Chapter 7 is all areas and volumes. They're all going to involve integrals. As I said in class, I would just set up the integrals at this point. That's the object of the game right now. Can you set up the correct integral or integrals to find this area or volume they're asking you to find? And then I would use the TI to evaluate that integral. You can also use the TI to find points of intersection of two curves if you want to save a little time there. Make sure you can do it by hand. Also, if the functions are difficult to graph, feel free to use the TI to graph them. Okay, so here's number 6. They give you the actual graphs, but they don't give you the points of intersection. They do give you the equations of the graphs. So g of x is the green line, f of x is this cubic curve, which has been moved to the right one. Of course, you're going to first need the points of intersection because, as you can see, the curve is above the line, and then over here the line is above the curve. So they're both equal to y, so we set them equal to each other, bring them over to one side, factor out the x minus 1, la 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 la, and we find out they intersect at x equals 0, at x equals 1, and at x equals 2. So again, top minus bottom. Here, the black curve is on the top, f of x, minus the bottom, which is the green line, g of x. But on the other side, from 1 to 2, then g of x is on top, f of x is on the bottom. So then you'd replace f of x and g of x and g of x and f of x. Take it from there. At this point, though, I would just pick up a calculator. Okay, number 7 through 14, the integrand. Now we're working backwards. Instead of them giving you the picture, you got to come up with the integral. They're giving you the integral, you got to come up with the picture. The integrand of the definite integral is a difference of two functions. So you'll notice you have a function minus a function. Sketch the graph of each function and shade the region whose area is represented. They don't want the area, they just want you to shade it. So my top graph, I'll call it f of x, is 1 minus x squared, which of course you know looks like this. And my bottom graph is, I'll call it g of x is x squared minus 1, which looks like this. You are going to need those points of intersection. And when you solve the system, set them equal to each other, you get plus or minus 1. So, as it turns out, when you plug 1 or negative 1 into either equation, you're going to get 0. So they actually intersect at their points, at their x-intercepts, which happen to be the same. And that's all they want is a picture. 15 to 16, determine which value best approximates the area of the region bounded by the graphs of f and g. Make your selection on the basis of a sketch of a region and not by performing any calculations. This is typical on AP. Okay, so the two functions in number 16 are f of x equals 2 minus a half x and g of x equals 2 minus root x. So obviously this is a line. Plug in x equals 0, you'll get y equals 2. Replace y by 0, you'll get x equals 4. So that's pretty straightforward. Y equals 2 minus root x. Well, of course, here's root x, which is that half sideways parabola. Negative root x, you'd flip it over the x-axis, and then we move it up 2. And again, I'd find the x and y-intercepts, not very difficult to find. You already have the y-intercept, x-intercept. Replace y by 0, you'll find out that x is 4. Now, so it turns out that they intersect at 0, 2 and at 4, 0. They intersect at their two um, intercepts. So we're looking for this little teeny skinny region right here. Graphically, if we look at this triangle that we have, which has one leg of 2 and the other leg of 4, the area of that triangle is 1/2 leg times leg, which is 4. So obviously this little sliver is very much smaller than 4. 6 wouldn't make sense, 4 wouldn't make sense. The area can't be negative, and also the integral is not going to be negative because everything's above the x-axis. Your choices are then 1 and 3, but it's tiny, so it would have to be 1. Okay, 19 through 36, sketch the region bounded by the graphs of the algebraic functions and find the area. So now it's up to you to sketch the graphs, okay? So there will be questions without calculator. They will expect you to graph some basic things. So first of all, this one is a line. So we place x by 0, you'll get y equals 10. I didn't even bother finding, if I replace y by 0, this would be 20, so 20, 0. Okay, this up here, they're giving it to you in this form, which is interesting because if you multiplied it through, distributed, you'd see it's a parabola. But actually, by giving it to you in this form, you can easily tell the y-intercept, because if I replace y by 0, since this is a product, either x is 0 or x is 8. Now, we would need to know how far up our parabola goes, because does it, is it below the line? Is it at the line? Is it above the line? Now you would distribute through. Remember your formula for the vertex, negative b over 2a. It turns out that that's 4. Plug 4 into your equation and you'll get 6. Whereas if you plugged 4 into this line, you'd get 8. So obviously the parabola is below the line. Okay, so it's bounded by this green parabola, the red line, and these two vertical lines. By the way, if you did try and find their points of intersection, you would find out there are none, as you can see. But we do have a shaded region because it's bordered on the top by the red, on the bottom by the green curve, on the left by the vertical line x equals 2, and on the right by the vertical line x equals 8. And of course, it's pretty obvious that the top curve is the red line, the bottom curve is the green parabola. And so it's the integral from 2 to 8 of top minus bottom. There's the line minus the parabola, and then I would use your TI. Okay, now we've been doing this in terms of x. Remember, our region has been bordered on the left by the vertical line x equals a, on the right by the vertical line x equals b, on the top by the function f of x, and our bottom border has been the x-axis. But everything's been done in terms of x in this case, which means we're actually looking at little vertical strips if you were thinking like Riemann sums, okay? So, but your function is not always going to be in terms of x. Sometimes it'll be in terms of y, such as x equals y squared. Here's an example. In this case, to find the area, what you're going to do is don't change the function into terms of x. Leave it in terms of y. So this will be dy, this will be g of y, this will be y equals and y equals. Well, y equals are horizontal lines. So this represents the bottom border, this represents the top border. This represents the right border, the function itself, and the left border is going to be, I have it down here somewhere, the left border is going to be the y-axis instead of the bottom border being the x-axis. So now you're going to have little rectangular strips, but they're going to be horizontal. So what happens is you have a region bordered on the right by the red parabola, on the left by the black curve, and on the bottom and top by these two green lines. So that's the blue shaded area. What you're going to do is set up an integral that goes from the bottom border of y equals 1 to the top border of y equals 6, and then you're going to do right border, which in this case is our x equals y squared, dy. Okay?